Hello, my name is Marek Ryklik and I'm the CEO of Xoralgo Incorporated. Today I will talk about a quintuple parity error correcting code and why it's a game changer in data protection. First, let me introduce myself, Xoralgo, and talk a little bit about the patent. Xoralgo Inc. is a University of Arizona startup formed in 2018. The technology is based on the U.S. utility patent awarded in May 2021. The assignee is the Regents of the University of Arizona, and the priority date is January 24, 2017. In addition to being the presenter, I am a professor at the University of Arizona Mathematics Department, and I'm the co-inventor on the patent along with my student. And I'm the CEO of Xoralgo Inc. The next part of the talk is about PentaRAID and its error correcting code. PentaRAID is Xoralgo's RAID implementation. A good starting point to our discussion of PentaRAID is the notion of undetected disk errors or UDE. These are exactly the errors which are undetected by the disk controller of a hard drive. They occur during normal operation due to the laws of physics. Their frequency is 1 error per 10 to power 14 or 10 to power 15 reads. For data rate of 1 gigabyte per second, a UDE occurs in 10 to power 5 seconds or 2 days. RAID 6, with one failed disk, remaining online and operating in degraded mode, takes weeks to recover with big drives of today, and during that period, every UDE becomes data loss. In conclusion, data loss due to UDE is a common occurrence. In this talk, it's important to distinguish between two types of data loss, errors and erasures. Both terms are introduced by coding theory and have a precise meaning. In both cases, we read previously stored data and blocks of data at a time. We say that an error occurs when one of the blocks is incorrect, but we do not know which one. An erasure occurs when one of the blocks is incorrect, and we know which one. An erasure is called that because we just might as well assume that the corresponding data is zeroed out or erased. It should be pointed out that errors are synonymous with UDE. They occur at a random place and therefore result in a random block being changed. On the other hand, a complete disk failure results in one of the n blocks of data being missing, and we typically know that the identity of the failed disk, which means that the identity of the corresponding block is known. So how common are disk errors? In this slide, we're concerned with both erasures, that means complete disk failure, and undetected disk errors. On the left, we have a well-known study of Seagate 3 terabyte drives deployed in 2012 and followed to complete failure. It turns out that in 3 years, almost all disks died. This batch of disks was unusual, and Seagate advertises 0.35% per year failure rate with 5-year warranty. Also, 1% per year failure rate is independently reported. On the other hand, institutions, such as universities, retire disks in a few months. Under a heavy load, disks fail much sooner, and in fact, the risk of them failing becomes unacceptable in merely a few months. On the right, we're trying to estimate the time to the next undetected disk error. In a laptop or desktop, we estimate that the next UDE will occur in 30 hours, and in a server under heavier load, it will occur in 1 to 3 hours, and in a very data-intensive big data artificial intelligence application, such as a self-driving car, this may occur in 1 to 10 minutes. UDE are especially harmful type of data loss known as silent data corruption, and the danger is that the loss is not known to the user of the data until the data actually is used. If the data happens to be in a sensitive portion of the application, a complete failure may occur. How many errors and erasures can PentaRAID correct? Let Z be the number of erasures and E be the number of errors. We have the fundamental inequality which says the number of erasures plus twice the number of errors has to be less or equal to 4 in order to be correctable. This means, for instance, that up to 4 erasures or failed disks can be corrected, and up to 2 errors or UDE can be also corrected. And please note that to be able to correct 2 errors, meaning UDE, we must be able to correct 4 failed disks. This relationship is a law that applies to all storage systems, and the difference is the number on the right. So 4 is specific to PentaRAID. How many errors or erasures can RAID 6 correct in comparison? It turns out that there is a similar law which says that the number of erasures plus twice the number of errors cannot exceed 2. This means that up to 2 erasures or failed disks can be corrected and only 1 error or UDE. This is why RAID 6 will lose data operating in degraded mode. Please remember that in degraded mode, Z is 1. That means we have 1 failed disk, and we operate in this mode for weeks in order to reconstruct the data on the failed disk. During that period, any additional UDE that occurs, which occurs every 2 days or so, will be converted to irrecoverable data loss. On this slide, we have a description of PentaRAID for an impatient expert. PentaRAID is a RAID based on a linear systematic forward error correcting code with n less or equal to q minus 2 data words and fixed k equal 5 parity words if Galois field in use is GFQ. Our code is not a maximum distance separable or MDS code, and its distance is 5. For example, if GF256 is used, we can have 254 data disks and 5 parity disks for a total of 259 disks. What are the advantages of PentaRAID? PentaRAID offers greatly superior data protection as compared to RAID 6 without increasing computational complexity. PentaRAID offers an extremely efficient syndrome decoding algorithm as compared to, for example, Reed-Solomon coding. For the curious, the decoder does not use Chien search. Chien search is a trial and error method of solving polynomial equations and is responsible for high computational complexity of most error-correcting schemes. Let's focus for a moment on the mean time to data loss for PentaRAID. Mean time to data loss is a standard measure of reliability of a storage system. Under realistic assumptions on the number of disks, UDE rate, etc., we find that the first bit of data will be lost by PentaRAID in 100 quadrillion years. Since this number is so huge that it's hard to imagine, Let's use an analogy. That number is comparable to the number of atoms in a gallon of milk or the number of stars in a visible universe. Let me discuss PentaRAID implementation and Xoralgo's first storage appliance. We have a reference software implementation where RAID is implemented in user space as a C library under Linux. It's exposed to the Linux OS using NBD protocol and in NBD kit from Red Hat. In particular, storage is exposed to the OS as a block device, can be used raw, partitioned, or used as a partition. The storage can be exposed as network storage using NBD. We offer in software PentaRAID along with RAID 0, 1, and 6. The user can format and partition the storage as if it were a single disk. The original implementation was ahead of the patent, and it was in year 2017, and it used NBD Kit version 1. The new implementation, 2021 implementation, uses NBD Kit version 2 protocol. A Xoralgo storage appliance and a test bed is an industry standard server with a RAID controller operating in JBOD mode. We offer software PentaRAID implementation, and we achieve approximately the performance of RAID 6. We offer vastly superior data protection. The product will be commercially available in 2022. Let's say a few words about testing PentaRAID implementation. Of course, we cannot wait 100 quadrillion years for an error. We must speed things up. We use the following simulation strategies. In simulation 1, we inject multiple random errors into physical or virtual disks. In a simulation number 2, we perform a disk removal test. Simply a number of disks is removed from the system. In simulation 3, we run operating systems on PentaRAID storage with a variety of demands and applications. Let's consider disk removal testing. In this test, PentaRAID with 15 disks was subjected to disk removal. These are real results obtained by automated testing of PentaRAID library implementation. In this test, a varying number of disks from 1 to 4 was removed from the system, and PentaRAID was tested for accuracy. Various combinations of parity and data disks was considered. As you see, all tests completed with OK status, meaning the data was 100% accurate upon retrieval from the storage. We find that running Ubuntu Linux on PentaRAID is an excellent test of PentaRAID's abilities and performance. In this test, we utilized Oracle's VirtualBox. Ubuntu is installed in a virtual machine with a 20 GB PentaRAID hard disk. In this particular test, we used the swap partition living on PentaRAID hard disk and evaluated its performance. In other tests, we played video games and tested specific applications. It should be noted that even in heavily degraded mode with 1, 2, 3, or even 4 disks missing, PentaRAID offers excellent performance and support for the operating system with minimal degradation of performance. We're planning future high-performance implementations of PentaRAID. For instance, software implementations will include kernel module implementation for Linux and a Windows 10 or 11 driver. Hardware implementations will be built for extreme performance. An FPGA-based PentaRAID controller, finally leading to an ASIC, will be produced. The fastest way to make PentaRAID available to the market is to license the technology to hardware and software vendors who already implement RAID controllers. We're open to that, and partnerships are welcome. PentaRAID fits well in the usual erasure coding workflow. We recall that erasure coding technology typically consists of a grid of nodes with disks attached to them. In the workflow, the data is fractioned and sent to the storage nodes, which subsequently spread the data across different disks within the grid. Storage nodes use ECC to reduce replication, and PentaRAID can be that ECC and excel at this task. PentaRAID is a drop-in replacement for other types of error-correcting code. Let me discuss this example in which Reed-Solomon code is used for data protection. In this example, 3 parity chunks are combined with 6 data chunks to form a data stripe. This configuration is not able to correct 2 UDEs and therefore is a very weak protection scheme as compared to PentaRAID. Therefore, by replacing Reed-Solomon with PentaRAID, we will get superior data protection. For instance, in that configuration, by replacing Reed-Solomon codes with PentaRAID and increasing the number of data chunks to 10, combining it with 5 parity chunks, we achieve the same redundancy overhead, but the data protection is vastly increased. So, is PentaRAID a game changer? What can it do for the storage industry? Is there a way to convert its powerful error-correcting ability, measured in mean time to data loss of 100 quadrillion years, into a tangible benefit today? Let's make a case for PentaRAID at large data centers. There is no longer a case for storing data in triplicate versus using strong ECC. The high computational complexity argument against ECC is defeated by the low complexity decoding algorithm for PentaRAID. Reducing the number of spinning disks by 30% and increased data protection is an easy target. Also, retiring old disks later, for example doubling the time in service, will result in further savings. There is a case to be made for PentaRAID at a small business. The data protection of a large data center can be achieved in a small storage appliance. Any IT manager who's able to manage RAID 6 will be able to manage PentaRAID. It's as simple as, if a disk enclosure is blinking, replace a disk. This eliminates the latency of accessing one's business data associated with the cloud. For example, a small independent video producer may not want to be moving data constantly between the cloud and his workstation. This results in significant cost of storage reduction and various optimizations of the workflow of the small business. Let me conclude the current talk by giving you the contact information. You can always email me at the University of Arizona, or you can visit Xoralgo's website where you will find a contact form, and also you will find the information about Xoralgo's patent and the white paper explaining Xoralgo's technology. On this very last slide, I provide several references related to PentaRAID and to today's talk. First of all, there is the PentaRAID white paper, which is in the open domain, and it explains all mathematical aspects of PentaRAID. One point of interest is a discussion of a limited recovery from 3UD. I would want to point out that a system with only 5 parity disks cannot recover from 3UD. However, under natural assumptions on errors, a recovery is possible. I would also want to bring to your attention Peter Anvin's RAID 6 algorithm exposition, which is followed by the new RAID 6 implementations, including our own along with PentaRAID. We used that particular algorithm for comparison of PentaRAID and RAID 6. Finally, if you're interested in Reed-Solomon coding and its computational complexity, there is Sarah Mann's dissertation written at the University of Arizona and directed by me. It was published in 2013, and it's probably the newest exposition and comprehensive analysis of this algorithm. Please take a moment to rate this session. Your feedback is important to us.